Hello students, my name is Shashank Shekhar. So today is the sixth lecture of the chapter, that is haloalkane and haloarene. So in the previous class we have discussed this substitution reaction. In today's class I will be mainly seeing the stereochemical aspect of this mechanism. Okay, so what will be the stereochemistry of the resulting product? We will see to that. After that we will move to this elimination reaction. We will just see a glimpse of it, what it is, and we will discuss it briefly in the next class. Okay, so talking about this say our stereochemistry, so you must be aware about some terms, so we will discuss them first, then we will see that what is the impact, or you can say what is the product that are obtained and what is the stereochemistry of that product. So the first is the optical activity, second is chiral compound, third is chirality, fourth is enantiomer. These four terms you should know. Okay, these four terms you should be aware of what are these. Then we will see in the reaction outcomes. So we can have three outcomes: inversion, retention and racemization. Moving to the next thing, that what is the product of SN2 and SN1, that whether it gives inversion or whether it gives retention or racemization, we will see that. At last we will see the introductory part of this elimination reaction. Okay, now first of all, optical activity. So if you see a compound, we can have two configuration, three configuration, four configuration of it. So you must have studied it in hydrocarbon, the stereochemistry, stereoisomers, right? So we will talk about that only. So we will specifically talk about today enantiomer. Then we will tomorrow look at the distereomers also. So in some cases you can get distereomer product also. We will see more about it in the questions. Okay, now talking about this optical activity, what makes a compound optically active? So if you pass a plane polarized light, so you must have heard this term, plane polarized light. So basically, if I want to give a small description of it, so it is the light whose waves propagate, or you can say whose wave oscillate on one plane and not on multiple planes. So they are termed as plane polarized light. And how they are produced? By placing the original light at through Nicola prism. So if you pass your normal light through the Nicola prism, then it will make that light as plane polarized. And if it is passed through a solution of certain compounds, and if it and that light, if it is rotated, then such compounds are called as optically active compound. Okay, so if you pass a, say, plane polarized light, which is PPL, sometimes it is abbreviated as PPL. So if you are passed a PPL through a Nicola prism, and then through the solution of the compound, and if you found that okay, that compound is showing rotation, or you can see that light is being rotated or deflected to some angle, then in that case that compound will be termed as optically active compound. And the angle by which the plane polarized is rotated is measured by polarimeter. Okay, that at what angle it is rotated, or you can say deflected, that is measured by the polarimeter. Now there are two conditions. Okay, suppose this is the solution, this is our solution, light is coming. Now this light can deflect towards us or away from us. So if you see it like this, see it like this, okay, if you see it like this, suppose you are seeing this, the light is coming from here and it is passing. So after this passing, so if suppose the light comes towards you or deflects towards you, then you may say that it is left deflected. Okay, just respect to the direction of light, you can say that it is left deflected, otherwise it is right deflected. If it is left deflected, then it is, say, it is levorotatory. Okay, it is termed as levorotatory. And if it is rotated right, then it is termed as dextrorotatory. Now there is sign for it, positive sign for it. So if a compound is dextrorotatory in nature, then it has a positive sign before the degree of rotation. So suppose it is rotating suppose a compound is rotating a PPL by an angle of 550 degree, and it is doing it in left direction, or you can say clockwise direction, then you will put a positive sign against this 50 degree. This means that it is rotated, or you can say it is deflected at right for dextrorotatory. If it is levorotatory, then we will put a negative sign against it. and in that case it is rotated anti-clockwise. So how is it anti-clockwise and clockwise? How is it saying? So if you look from upward, and if you see that light goes from here, so it should be the actual path, and it goes like this, so it is considered as right. Okay, so in right direction it is considered as clockwise, because if you see from above, you will see that it is clockwise rotating. Okay, this is clear. Now such plus minus isomer of a compound are called as optical isomer. So we can have two rotations. Such two rotations are given by the same isomer of the same compound, not the same compound, the same formula, and that are called as optical isomers. And their deflection is same in either direction. Suppose if plus 50 is given by one of these, then minus 50 will be given by the other of these. And this phenomena is termed as optical isomerism. So this is clear. Okay, so what do you mean by optical isomerism? So if some compound is rotating a PPL, that is a plane polarized light, after passing through it, then the compound is termed as optically active. And they produce two kinds of rotation, clockwise and anti-clockwise. Depending upon the clockwise and anti-clockwise, it is termed as dextro and levo. And such compounds which do that are called as optical isomer, and this phenomena is called as optical isomerism. Is this clear? Now we have this chiral compound. So we have seen that, okay, so this is the optical activity. Now what is chiral compound? So chiral compound, so if I take an example of a chiral compound, suppose we have a carbon, so I'm just taking an example of it. Okay, so chiral compound cannot be just a carbon having 4 different groups. We can have different examples of this compound which are chiral, and which the carbon is not having the 4 different groups. But I'm taking one of those examples. Suppose a carbon has 4 different groups. Then if you take the mirror image of that carbon and try to put it on this superimpose, so you'll see what it is superimpose and all. Just keep this in mind. So if you take a carbon which has 4 different groups and reflect it through a mirror, then the mirror image that we got will not be superimposable on the first one. Means if you take the mirror image and if you take the real one and try to match them, or you can say that you try to shut them completely. Okay, just keep them completely aligned. Okay, that would not be possible. So in that case, that carbon is called asymmetric carbon or a stereo center, because due to this center we are getting the stereochemistry. So it is termed as stereo center, and it is also termed as asymmetric carbon. Okay, it is also termed as asymmetric carbon. Now the resulting molecule would lack symmetry and is referred to as asymmetric molecule. So what is this thing? So if you would, I would say that if a compound is having a carbon that has 4 different groups, such that the mirror image of that is not superimposable on this image, then we will term the carbon as asymmetric carbon, and that molecule is termed as asymmetric molecule. Now the asymmetry of the molecule along with the non-superimposability of mirror image is responsible for the optical activity in such organic compound. So what is being told here? So this is the why we have seen that, okay, due to the passing of this light through this plane polarized light through this solution, we see a deflection. So what is the reason for the arisal of this deflection? It is this chiral center, or you can say the asymmetric carbon, which is rotating the plane polarized light. Okay, so is this clear? So asymmetric carbon is not the only criteria for being for making a compound chiral. So it is one of the criteria. So we will see more about it later on, or you must have studied in hydrocarbons also. Now, what is superimposable? So I have told this word or mentioned this word superimposable. So if something cannot be placed on its mirror image, then it is termed as superimposable. Like this example. So if you take this example, you take your hand, make a mirror image of it. Now if you try to take this hand print and keep on this, then you will see that this thumb, you will see that this thumb will be coming on this little finger. Now if you rotate this by 180 degree, then still, now your back is different. Now we'll keep your back on this front one. So basically I mean that you cannot touch with everyone. You cannot do the corresponding thing. no matter how you rotate, okay, the compound with this will remain same, but how, it does not matter how it rotated, it will remain the same. You cannot superimpose it. Similar goes with your leg. But if you consider a glass, okay, and just a symmetrical glass which is having a plane of symmetry, if you just reflect it and you got a mirror image, try to keep on this, you can see that this has now completely covered this one. So it would be a better word. So if something is completely covering the other one, then it is termed as chiral, non superimposable. Okay, superimposable. So these are some example of non-chiral object. They are non-chiral because the mirror image is superimposable on each other. So examples are given. These are the examples. Now, chiral molecules are optically active, while the objects which are superimposable on the mirror image are called chiral. These molecules are optically inactive. So these are you cannot just think of molecule, you can think of the object around you also. So these are not chirally active, these are chirally active, or these are chiral molecule, chiral things, and this is achiral things. Now next we will see what is enantiomer. So initially we have seen that, okay, compound can rotate a light while left or right. Now the mirror image of that would do the opposite thing. So suppose I take an example. Suppose I take a butane tool and I say that, okay, this butane tool is rotating this specific structure of butane tool is rotating the light through left, okay, or you can say anti-clockwise. Now what do? You take the mirror image, you take a compound such that the structure of that compound is a mirror image of the previous one. Now you pass the plane polarized light, then you will see that the light is now rotated right, okay, or you can say clockwise. So such compounds, those mirror image are available and they are rotating the light in the opposite directions by the same degree, then they are termed as enantiomer. So if you see, you cannot just do it every time experimentally. So what do? We take the root cause of this, you can say, deflection of light, that is superimposability. So if you found that two compound of means the mirror image of a compound is not superimposable on its original thing, or you can say object, then you will say that, okay, it is optically active and they both are now enantiomers in that case only. So if you take this example, so here A and B, they both are mirror image of each other. Now since this carbon has do not have 4 different groups, so if you place one on each other, then they will be easily kept, okay, they can be easily kept on one another. Due to this reason, this and this are not enantiomer, while this D and E are your non-superimposable. So how this one is superimposable? So suppose you take the mirror image of it, now just rotate it. Try to imagine that you are rotating this thing. Now if you rotate it by 180 degree, you will get this thing back, which is equivalent to this one. So due to this reason, this compound is not optically active and it will not have enantiomer. Whereas this compound, if you take the mirror image of it and try to just rotate it, still you will find that you cannot superimpose it. So they only differ with respect to rotation of plane of light. If one of the enantiomer is dextrorotatory, the other will be levorotatory. Now what is racemic mixture? So we have seen what is enantiomer. So if we take, so if for a compound one and only one enantiomer is possible, okay. So if you take a compound, I mean that if you take a specific compound, is spatial arrangement is defined and you want to find the pair of it, so you can get only one pair that would rotate the light to the same angle, but in the different direction. Now if you take such enantiomer and mix them in equal proportion in a container, then you will see that they will show zero optical rotation, because one is trying to rotate it through right and the other one is trying to rotate it to left. And since we have taken the same concentration, this will be cancelled out and there will be no net rotation. You can think it of as a tug of war. So if you are pulling from the right side and similarly you are pulling from the left side, and suppose you are the person only doing the same thing on the both sides. This is just a hypothetical situation. So since you both are same and we are considering that, okay, there is no energy dissipation and all, So we will see that the rope will, or the knot which is been done there to see that whether it is pulled that side or this side, will not move by 1 inch. Okay. And due to this reason, due to the same reason, there is a cancellation of rotation in this case also. Now such a mixture in which enantiomer is present, and we say that okay, this is present in the same concentration, then the mixture which is formed is called as racemic mixture or racemic modification. So if you think of a racemic mixture, it is represented by DL or plus minus. So if plus minus is written in front of some molecule, then just assume that that compound is present in racemic amount. So for example, butane, if you write it like this, then you have a compound that is having both enantiomer. Okay. Now the process of conversion of enantiomer into racemic mixture is called as racemization. So if you take enantiomer and then add another enantiomer, that is a mirror image which is not superimposable, and keep adding on it till you do not get any rotation, then the process will be termed as racemization. So is this clear? Okay. Now how we will see what is inversion, retention, and racemization. Okay. So there are 3 cases. So if you react something with something, so this is our compound. This is our compound. Now if you react it with something, say we are reacting with Y, then 3 cases can arise. Okay, 3 cases can arise. First is your, say, what is this? This is your inversion. What is inversion? So if you see this compound, then you can see that this has been inverted. This one is being put here. Now since initially CH3 was here, now it is here. Okay, so it has been inverted. Then this is called as inversion. Now if you compare it with this one, you can see that this all things are same. This all things are same, except you have just changed X with Y. So this is kind of retention. And if both are formed in equal amount, then it is called as racemization. So these are the 3 examples. Okay, is this clear to you? Okay. Now, in what case we will see inversion, in what case we will see retention and racemization, that depend upon the mechanism of the reaction. So if you are doing a reaction and taking getting these things, then you can predict with the help of your product that whether that is SN1 or SN2. So let us see some examples. So first is our SN1. So suppose we take an active alkyl halide. Suppose the product formed is active alkyl halide. Now whether to check that it is SN1 or SN2, you can just see the product. So suppose this is our reaction, this OH minus is attacking here. Okay. Now you can see that there is a kind of inversion of this compound. You have rotated it through 180 degree. And how you have rotated it? Rotated it, just do it like this. Okay. On the plane, you do the in plane rotation. Okay. Now this Br will come here and this whole group will move here. The same thing is been done here. Only Br has been now removed by OH. So if you see here, so in these case, there is no change in configuration. Sorry, there is change in configuration. You have seen that there is kind of inversion and Br minus is released. Why has this happened? So if you remember the previous pictures, you must have seen in SN2 that this OH minus was attacking from back, or the nucleophile was attacking from back. So this is a back attack, and due to this case, you can see inversion. So imagine it like this. So you must have seen, so if you have faced high intensity winds and you take an umbrella and go out with that, say, do not try this at home. I'm just saying it for example. Okay, suppose you take an umbrella and go out in a strong wind, then you will see that due to high wind speed, this umbrella will just invert. You must have seen that. Okay. So that kind of inversion, that you can think of similar analogy. So that kind of inversion can be seen. So this happens in SN2 reaction because there is a backward attack and all this substituent just go in the opposite direction and we get opposite thing. So if you have remembered this RNS nomenclature, which we have taught in this hydrocarbon. So if I just say that, suppose number it. So this is first priority, this is second priority, this is third priority. So, and the hydrogen is in the lowest priority, is going inside the plane. So we do not need to worry about it. So it goes in this direction, which is clockwise. So it is R. So this one will be of course S. So what happens in inversion? Now R configuration changes to S configuration. Just see it. Okay, this is 1. Okay, this is 2. This is 3. So if you see it, is now in the opposite direction. This sense of rotation has been changed. So in this case it was like this, and in this case it is like this. So this is going from R to S, and then OH minus is kicking out your Br minus. So is this clear? Okay, now we are done with this SN1. Now what happens to SN2? So if I tell it directly, then racemization occurs. Okay, racemization. Why is it so? In case of actively active alkyl line, SN1 reaction are accompanied by racemization. Why is it so? Because it's formed in 2 slow steps. So we have to look at the mechanism and predict that how it happens. So first, what is happening here? This Br minus leave, and we are left with this intermediate. Now this is trigonal planar. Now both of the faces are equally vulnerable for the attack of this Br minus. Since it is equally vulnerable, they attack from both sides. Okay, they attack from both sides, and so this is the structure that we have. Okay, so see, this is our carbocation, and both of this orbitals are vulnerable. Now OH minus can attack from upside also and come from downside also. So they result in both plus and minus. Both plus and minus, and is a since the probability is equal, so 50-50, almost 50-50 product is formed, and we get racemization, due to which if you pass now a plain polarized light through the product solution, you will see no rotation. Is this clear? Okay, now next one. So this was all about SN1 and SN2. Okay, this was all about SN1 and SN2. SN1 and SN2 are over. So if you again give a quick revision of it, so we have seen that SN1 was a following second order kinetics, and it was good for say allylic, first benzylic, allylic 3 degree, 2 degree, and 1 degree, because better would be the stability of the tertiary of the carbocation, better would be the SN1. Then we move to SN2, in which we saw that okay, so if we put suppose if we take 1 degree, then it will give faster reaction. Why? Because it was having a back attack. A back attack was occurring. So less steric hindrance means it would go less steric hindrance means it would favor this SN2 type, and it was a say this thing, our for second order kinetics. Now it is, since it is a second order kinetics, so it will depend both on the concentration of the substrate and the reagent. Now how can we distinguish it? First, based on our say the substrate, whether it is primary, secondary, tertiary, benzylic and allylic. Then we can see other condition. If you are using strong nucleophile, then and if you see that okay, there is secondary carbocation, then the probability is that okay, this will go through your SN2. Now if you are all things are same, suppose the solvent is now different. One is having aprotic solvent, polar solvent, and one is having protic protic polar solvent. Then aprotic will give you SN2 and protic will give you this SN1. Is this clear to all of you? Okay, but all this condition you will then apply if you see a 2 degree, because first and the deciding factor is 3 degree, 2 degree, 1 degree, that thing. Now if you see a 2 degree, then it is in the middle of 3 degree and 1 degree, then there is a confusion. So in that case you will see other things. So this was the thing. Now since there was a back attack in case of your SN2, there is a inversion of this configuration, means R changes to S, because there is a back attack. Now if there is not a SN2, then it is SN1, and since the carbocation that is formed is vulnerable from attack from both sides, that is upside and back side, therefore it leads to both of the products S, R and S, and this leads to racemization because the probability of attacking from both sides are equal. Now we will focus on one more type of this substitution nucleophilic, which is termed as your SNI. SNI. So what is this SNI? So you must have seen this reaction earlier. CH3, CH2, OH and SOCl2. So this was used for the preparation of alkyl chloride. So this is a kind of SNI. What happens in this reaction? What happens in this reaction? So first this O will attack this S, and this one of the Cl will be given out. Okay, you get this kind of thing. Now you are kicking out this Cl minus. Now this Cl minus will attack here. Okay, and this would lead to this thing. Now if you see here, okay, if you see here, so this is not this reaction, sorry, it will happen like this. Now this Cl will attack. This Cl will attack here, and your SO2 will be released. So it is happening it is a kind of self substitution. First your adduct is formed. Okay, that is clear. But now after that, we see a self substitution, means the Cl is substituting this whole of this group, and you got your CH3, CH2, Cl. Now if you see this thing, this reaction, this is a kind of retention. Okay, this is a kind of retention here, because there's no back attack or something like that. So there is a retention of the stereochemistry. So you have seen three things: racemization and inversion and retention. So that racemization is a product of your SN1. Then the retention is racemization is a product of this SN1. Your inversion is the product of your SN2, and your retention is the product of your SNI. So we'll study this SNI with the help of examples more. Okay, then we will move to this elimination reaction. Okay, so this is our elimination reaction. So what happens in elimination reaction? So when you take a haloalkane with beta hydrogen, and heat it with alcoholic KOH. Beta halogen means, what is beta halogen? Beta hydrogen atom. So when an haloalkane with beta hydrogen, so this is our haloalkane. Okay, this is our haloalkane, and you can see at the beta position of this, so these are the two beta positions available, 1 and 2. There are hydrogens. Okay, so there is an elimination of hydrogen atom. So if you put a base, then it is possible, or if you put a nucleophile in some case also, they do not act as nucleophile and take this hydrogen and act as a base. And further, this Br also leaves, and we get an alkene. So it goes like this. Suppose you have your compound which looks like this. Okay, which looks like this. Now suppose your base comes and take this hydrogen, then it will go like this, and you will result in getting this thing, alkene. So this is called as beta elimination. So we'll talk more about it. Okay, now this beta elimination, in case of symmetric, there is no difficulty. But if the alkene that is formed in an asymmetric molecule, then it is then there is a case of then there is a possibility of two different products. Okay, now this was finalized by SATHEE-MED rule, and SATHEE-MED said that, so the two possibilities are there. Okay, so two possibilities, and both of the possibilities are possible, but in different cases depending upon the substrate, reagent, and you can say conditions. So here is an example. So generally we get more substituted alkene. Okay, so there is a possibility of formation of more than one alkene due to availability of more than one beta hydrogen. Usually one alkene is formed as the major product. So this form part of a pattern which observed by Russian scientist Alexander Zaitsev, which is pronounced as Zaitsev, who in 1875 formulated a rule which can be summarized in dehydrohalogenation. So you can see bromine and hydrogen are removed simultaneously. The preferred product is that alkene which has the greater number of alkyl group. Okay, so this one has the greater number of alkyl group attached to it. So due to this reason, it is showing this pentane 2-ene. But in some cases you will see that, okay, this is not formed, instead this is formed. This is not the case, but you will see it. There are some examples. Okay, is this clear? Now we'll see more about this elimination reaction in the next chapter, in the next lecture, I would say, where we will see E1 elimination, E2 elimination, and plus E1 CB elimination. At last, we will see the reaction with metal, and with that, we can end our chapter. Okay, so these were the these are the two types of reaction that I have till now introduced, and the last one is remaining is reaction with metals. So this is clear? Okay. So with this, I would like to end my lecture. Thank you for attending it. Thank you.